Today, we're going to tackle a question that sounds super simple on the surface, but getting it wrong can have literally million-dollar consequences for a company. Let's jump right in. Okay, put yourself in the hot seat for a second. You're the boss, and you have to make this call. You're about to spend millions of dollars on a brand new fleet of delivery trucks. These things are going to be the backbone of your company for years. So what's the magic number? How many do you buy? I'm not kidding. Getting this one number wrong could literally sink your business. I mean, think about it. If you buy too few trucks, you can't keep your promises to your customers. But if you buy too many, well, you're just burning cash on shiny, expensive trucks that are just sitting there doing nothing. And here's the crazy part. There is an easy way to figure this out. Some simple, logical, back-of-the-napkin math. But, and this is the twist, that obvious calculation, it's a trap. And it's a trap that costs companies millions and millions of dollars. So let's break this down. This really is a classic logistics puzzle, a true million-dollar question. Okay, so here's the setup. We've got a company shipping stuff out 365 days a year. Now, their demand for trucks swings wildly. I mean, one day they might only need 20 trucks, but the next they could need up to 65. Over the whole year, that adds up to a whopping 14,600 deliveries they have to make. No excuses. And this is the tightrope they have to walk, right? It's a real balancing act. On one side, you've got the disaster of not having enough trucks. You start missing deliveries, customers get angry, and your reputation goes down the drain. But on the other side, you've got this money pit of having too many trucks, just sitting in a parking lot, losing value every single day while you're paying a fortune for maintenance and insurance. It's a tough spot. So how do you avoid both of those nightmare scenarios? Well, most people's first instinct is to just do some simple math. And that is exactly where the trap is. Okay, look at this. This feels so logical, right? It makes perfect sense. You just add up the average time for every single step. You've got loading, travel to the customer, time at their site, travel back, a quick inspection. They even averaged out the repair time. And what do you get? A nice clean number. An average round trip takes 40.6 hours. Super straightforward. What could possibly be wrong with that? So we've got our average trip time, and we know our total demand for the year. A little quick math, back-of-the-napkin style, and bam, you get a very confident-sounding, very specific answer. 68. The math is just so clean. You take the number of hours in a year, 8,760, divide it by that 40.6-hour average trip time, and you figure out that each truck can handle about 215 trips a year. To cover all 14,600 loads, you need 68 trucks. Simple. Perfect. Case closed. Right? Okay, this right here, this quote is our first big clue that something is very, very wrong. See that phrase, lower bound? What does that mean in plain English? It means 68 is the absolute best case scenario, everything goes perfectly number. It's the bare minimum. So it's our starting point, not our final answer. So if the simple math is a trap, how in the world do we find the real answer? We have to build something smarter. We have to build a digital twin. Because here's the thing, the real world isn't average. It's messy, it's chaotic. That neat 40.6-hour trip time, that's a fantasy. Some trips are faster, sure, but a lot of them are going to be slower, thanks to traffic, bad weather, you name it. That's the key word right there, variability. And it is the mortal enemy of simple math. The tool we use to fight back against all that messiness is called simulation. And honestly, the best way to think about it is like a super advanced video game for the business. We build a perfect virtual copy, a digital twin, of the entire delivery network. And then we can run it thousands, even millions of times, testing it against all that real-world chaos without risking a single penny. And this is what makes it so powerful. It doesn't use one single, simple average. No. It uses ranges, just like in the real world. The simulation knows that demand can swing between 20 and 65. It knows travel time could be a quick 4 hours or a brutal 30 hours. It even knows there's a 10% chance a truck will need a major repair. It doesn't ignore the chaos, it embraces it. All right, our digital twin is built. Time to fire it up and put it through its paces. Let's run a virtual stress test and see what really happens. And boom, here's our first bombshell result. On the left, that's our simple math fleet of 68 trucks. In the simulation, guess what? It only handles 13,832 trips. That's, almost 800 missed deliveries? That's a disaster.
On the right, that's the absolute max potential if we had a magic, unlimited fleet. The gap between them is huge. This proves it beyond a shadow of a doubt. 68 trucks is nowhere near enough.
So what the simulation does is test a whole bunch of different fleet sizes, all the way from our starting point of 68 up to 144. And look at this curve. See how steep it is at the beginning? Going from, say, 68 to 75 trucks gives you a massive boost in performance. But then, look what happens. The curve starts to flatten out. That's the classic point of diminishing returns. You're adding more and more expensive trucks, but getting less and less bang for your buck.
So this is it, the million-dollar question. We know 68 is too few. We know 144 is way too many. The answer, the perfect fleet size, is somewhere on that bend in the curve. But where exactly is that sweet spot? Where's the perfect balance?
All right, let's zoom in on that critical point of the curve. It's time to put the final contenders head-to-head and find our answer.
So, after all the analysis, it really comes down to this: a fleet of 70 trucks versus a fleet of 75. The simulation data is clear. Adding those 5 extra trucks means you can complete an extra 265 trips over the course of a year. Now, those 265 extra trips, that works out to a 1.9% increase in performance. So here is the final, bottom line question. Is it worth buying 5 more really, really expensive trucks for a 1.9% boost? And this is where a really smart business rule makes the decision for us. You see, management had already set a threshold. They decided that any performance gain over 1% was operationally significant. In other words, it was a big enough improvement to actually make a real difference to the company's profits. And since 1.9% is obviously bigger than their 1% threshold, the decision is crystal clear. Those 5 extra trucks are absolutely worth the investment. The simple math trap would have led them to disaster with 68 trucks, but the data-driven simulation, it gives us the right answer, the profitable answer: 75. So there you have it. We've solved the puzzle. But you know, the biggest takeaway here isn't the number 75. It's not really about the trucks at all. It's about how we found that number. Because this exact same thinking, this idea of using a digital twin to account for all the real-world messiness, you can apply it to almost anything. Think about it. How many nurses does a hospital need on a Saturday night? How much inventory should a retail store stock before a big sale? How many people do you need working in a call center? It's the same problem. Because ultimately, it all boils down to one huge question. How do you balance cost against performance when you live in a world you just can't predict? The answer is, you can't rely on simple averages anymore. You have to embrace the chaos, embrace that variability, and use smarter tools like simulation to find that perfect sweet spot. That's how you turn a million-dollar guess into a data-driven decision.